All right, everybody. So what we're going to be looking at today is going to be section 10.2 in your book. And what this is going to be graph terminology and also some kinds of special graphs. And special graphs. Which I think I mentioned in the previous video that there were like special graphs. I think we talked about like a cube or something. But it'll take us a while to get there. So let's go ahead and start with the book here, the book definitions. So just so we know what we're talking about here, we've got vertices like this. We talked about that last time. And we've got some kinds of edges that may be between these, and that makes a graph, right? So this is a graph. Technically, I guess this would be like a pseudograph or something, or a multiple graph at least, because I have multiple edges at some point. Okay, yeah. So let's label the vertices here real quick. Let's call them V1, V2, V3, V4. All right, and just so we can have a graph to refer to when we're looking at these definitions. All right, so let's get started here. So we're going to start with graph terminology. So our first definition in this section, definition 1, is going to be for adjacent. So I probably already used these terms before, but I'm going to, use them again. So, or precisely define them. So, two vertices, U and V. That's how they're often referred to in definitions. U and V in an undirected graph. Probably a directed graph as well, but undirected graph, G, are neighbors. So there's a word, neighbors, if U and V are endpoints of an edge. E in of G, actually, is what I wanted to say there. I was going to try to shoehorn something else in. Right? So it's a very simple definition. There's one more thing we want to there, which is going to be the edge E is incident with, I was going to write 2, but with the vertices U and V. So what are neighbors and what is incident? So an edge is incident. An edge is incident to the vertices, and the vertices are neighbors if there is an edge between them. It's not like this is some complicated thing, but still. So like on this graph right here, you could say that, V1 and V2 are neighbors, right? And why? Because right there's an edge connecting V1 and V2. You could also say something else. We could say, if I labeled an edge here, like let's just call this E1, E2, E3, E4, we could say E1 is incident with V3 and V4. Okay, so these aren't like super complicated definitions, but that's just the language that you use to refer to these graphs, right? How do you say what you want to say? So there's a precise way to say that an edge is connecting two particular vertices, and two vertices are connected by a single edge, right? That's neighbors. All right, so let's move on. Definition 2. So definition 2. The set of all neighbors of a vertex is called, what do you think it's called? The set of all neighbors. It's called a neighborhood. Actually, the neighborhood of V. Okay, so they give like some definition involving set theory, how to come up with that, but I don't think we need it, right? So, like in that graph up above, we could say, what could we say about it? The neighborhood of V3. What's the neighborhood of V3? So the neighborhood of V3 is going to be all of the vertices that are adjacent to V3. So it looks like just V2 and V4, right? Because in this graph right here, V1, right? V1 is not directly connected to V3, so it's not in the neighborhood. But V3 is connected to V4 and V2, so they are in the neighborhood. So that's it, really. Neighbors. Degree of a vertex. So this one's going to be important, the next definition here. So definition 3, put like a little box around it, highlight it. So you need this one a lot. The degree of a vertex, which I think we counted that up last time, right? But we'll do it again. The degree of a vertex of an undirected graph is the number of edges incident to the vertex or with it, except a loop at a vertex contributes twice. To the degree. All right, and we write it this way. DEG, like V. That's how you would write the degree of a vertex. The degree of V. So let's just draw a little graph here. I guess let's call it H because we use G for something else. Okay, so there's a graph, and let's just label the vertices V1, V2, V3, V4. Okay, so we got some vertices there. Let's find a few degrees. So let's say, example, let's do the degree of, let's just do V1 and V2. Actually, if we're doing that, we might as well just do all of them. All right, that's a 2. Okay, so let's find all of these degrees. We can do that because this is undirected, right? There's no arrows on the edges. That's what directed means. So in the definitions, when they say undirected, they just means no arrows on the edges. All right, so let's count this up. So I think we've done this before, but we'll do it again. So like for V1, which is right here, you just count up the edges that are leaving that vertex. So you just go 1, 2, 2 of them. So that is the degree 2. All right. Then, oops, that's not quite what I wanted. You do the same thing for V2. V2 is a lot harder. And you basically have to remember to count loops twice. So if I'm counting this, I'll count. This is the first one incident to V2. This is the second one. This is the third one. This is 4 and also 5. Because the loop actually counts double. So you count the loop where it leaves the vertex and also where it comes back in, is the idea. So what's the vertex of V2? It is 5. Okay, so let's move on. Let's do V3. So V3 is just 1, 2, 3, 4. And then for the degree of V4, it's just 1. That's not what I wanted. 1. So 1. So that's how you find degrees. The only hard part is remembering to double count, like I said. Okay. What else can we say about it? I think there's a theorem that I want to do. How far down is it? Yeah, it's the next theorem. Awesome. So we're going to have a theorem now. So we've got enough definitions that we can have a theorem. So I know that I promised you in a previous lecture that we were done with proofs, and we basically are. But, you know, we still have theorems, and the theorems could still be proved, but you don't have to prove them. And actually, I don't think I'm going to prove this either. I think it's harder to prove than you think. So theorem 1, let's have it. It's called the handshaking theorem. It goes, never shake hands. They're trying to give you COVID. The handshaking theorem. So let G equal V comma E. So remember that graph is defined with a vertex set and an edge set. So that's what V and E are, the vertices and the edges. Be an undirected graph, because we haven't talked about directed graphs. With, and this is important, in edges, because this theorem is going to deal with counting edges. So you need to know how many of them there are. So let G be a graph with n edges. Then 2m equals, wait, why am I using, okay, m. 2m equals the sums of the degree of v. And that's for all of the v's in v. So that's a little bit kind of unusual language here. You guys have mostly taken Calculus 2, so you should be familiar with this, right? This is sum, and this means all the vertices, which are the little v, vertices little v that are in the big V, which is the vertex set. Okay, so what does this mean? It just means if you add up all the degrees, you get double the number of edges. So if you add all of the degrees, I want to write that differently. If you add the degree of each vertex, the result is twice the number of edges. Or you could say that a different way as well, right? If you double the number of edges, or yeah, I don't know. You could say it this way too. add up degrees and divide by 2, that's how many edges there are. Right, so there's lots of ways to say it. It's an important theorem. One of the things it does is it actually tells you that some degree sequences are not possible. Because this tells you that if you add up the degrees, you have to get an even number. So if you add up the degrees and you got an odd number, then you would have a problem. Okay, so a consequence of this is this other theorem, which I'm going to write down the other theorem and then we'll look at it. But so this is a different theorem technically. It's really kind of a corollary actually, because it comes straight from that previous theorem. Corollary. An undirected graph has an even number of vertices with odd degree. That's an awkward way to say it, but let's look at it. So first of all, let's just look at the previous theorem just involving degrees. So let's take this graph here. How do I do that? Lasso. Duplicate. Move it down. Okay, cool. So like for example here, right? We added the degrees here, I think. Let's oops. Okay, fine, we can't do it. Good enough, good enough. All right, so we have all the degrees of this vertex, right? So this is going to be an example. So, right, we had these degrees. Right, the degree of V1 is 2. The degree of V2, if I remember correctly, was 5. The degree of V3 looks like 1, 2, 3, 4. And the degree of V4 is just 1, right? And so you add these up. Of course, very easy to do. You get 2 plus 5 plus 4 plus 1. So what do we get? So the sum of the degrees of V are going to be 2 plus 5 is 7, 7 plus 4 is 11, 11 plus 1 is 12. So you have 12, right? So that means, so 2m equals 12, or m equals 6. That's the number of edges. According to the theorem. Right, so is it? Well, let's just count the these edges, right? So we got 1, 2, 3, 4, 5, 6. So yeah, it works, right? So 6 edges, sum of the degrees is 12. And so that's the way the theorem works. Now, what that means is that you can't have certain degree sequences, because the result, like when you add this up, it has to be even, right? This will always be even. Because it has to be twice the number of edges. So if it was like 13, then 13 over 2 is 6.5. But a graph can't have 6.5 edges, right? So that means that the sum of the degrees can't be an odd number. that's what that previous corollary tells you. So like they'll ask you questions like that in the book. They'll say like, can these degree sequences exist as undirected graphs? With multiple edges and loops allowed. Right. So can they? Well, let's write a few of them, right? So let's do like A. 1, 2, 2, 1. And they usually do them this way, where they just list some numbers. Let's do, I don't know. I'm trying to think. 3, 3, 3, 3. 1, 1, 1. Actually, let's change this one. Sorry. 1, 3, 1. Okay, so let's try to do this. Okay, so generally we can use the theorem, and we could also try to draw the graphs. So let's use the theorem first. So if you sum these up, so sum the degrees first of all, just to see what they are. So if I add up those degrees, right? So this is supposed to be like the degree of vertex 1, the degree of vertex 2, the degree of vertex 3, the degree of vertex 4, because these are degree sequences. So add those numbers up. So 1 plus 2 plus 2 plus 1. Is that 6? It's 6. Okay? Which is, of course, even. And the next one is 3, 3, 3, 3, which I think is 12. So that's even. And the last one is 1, 3, 1, which is 5, which is odd. Right? So what that tells you is that we should be able to draw graphs for A and B, but not for C. So there should be graphs for A and B, but not C. And if you go to try to draw these, you'll see that that's the case if we try to do it. So let's try it. So let's try to draw the graph for A. Now I say the graph, but really there's going to be probably mini graphs. So like V1, V2, V3, V4. And it takes a couple tries sometimes. So 1, 2, 2, 1. So V1 is supposed to have degree 1. That means one edge coming out from it. So, okay. Now we're done with V1. Now, V2 is supposed to have a degree of 2. That means 2 edges should be coming out of V2. So we've already got one of them, so we should draw another edge coming out of V2. Now, where does it go? Could go down to V4, could go down to V3. It can't go back to V1 because then V1 would have another edge, which would make its degree 2 instead of 1. So V2 has to have an edge down here to one of these. It doesn't matter which one, but you gotta, pick. So I'll just go here. All right. So now this has degree 1, which it's supposed to have. This has degree 2, which it's supposed to have. Right now V3 has degree 1, right? 1, because I drew it. It's supposed to have 2. So V3 needs another edge coming over here to V4 probably. Now V3 has degree 2, and V4 has degree 1, which it does, so that's fine. So there's a possible graph for A, right? The degrees are 1, 2, 2, 1. 1, 2, 2, 1, just like I drew up here. 1, 2, 2, 1. That's going to erase. Okay. But this should be true for the next graph as well. We should be able to draw it. So let's try it. 1, 2, 3, 4. Again, let's just call them V1, V2, V3, V4. Let's try to draw these. So I'm going to try to avoid multiple edges if I can, and loops if I can. I kind of use loops to kind of fix things at the end if I need to. So V1 is supposed to have degree 3. So V1 needs to have 3 edges that come out of it. So you could draw them like this. 1, 2, 3. That's one way to do it. You could also do a lot of other things as well, though. You could do 1, 2, 3, because a loop counts double. And then like that. And we could do that. That would work, right? Because a loop counts double, so that loop is 2 and then 1, so that's 3. And then that loop's 2, oops. That loop's 2 and then 1, so that's 3. And that's 2 and then 1, and that's 3. And that's 2 and that's 1, and that's 3. So that would be 3, 3, 3, 3. Erase all this. We could draw this one where we go 1, 2, 3. So V1 has degree 3. And then V2 has right now 1, but I can go like that, and that's 2, and then like that, and that's 3. And then V3 is supposed to have 3. It's got 2, so I can draw this, which would make it 3. And there you go. So that'll work as well. So we had, multiple possibilities for the graph with the same degree sequence. So more than one graph with the same degree sequence exists. Right? So it's not the graph, it's just a graph with that degree sequence. 3, 3, 3, 3. All right, so let's try the last one. C. So we got 1, 2, 3, 4 vertices. No, we have 3 vertices, don't we? I don't know why I did that. Actually, I'm going to come back here. I'm going to just change the number here. 1, 3, 1, 2. All right, which is 7 now, which is odd. That's just so we have the same number of vertices, right? Because the number of vertices was not what was important. V1, V2, oops, V3, V4, right? So the claim is that we can't draw this graph. So if you try, like vertex 1 is supposed to have degree 1. So you go, okay, like that, maybe. Vertex 2 is supposed to have degree 3. So you say, okay, maybe 2, 3. All right, so vertex 1 and vertex 2 are okay. Now vertex 3, oops, where's the pointer? Vertex 3 is supposed to have degree 1, which it has. So right now, vertex 1, vertex 2, and vertex 3 are 1, 3, 1, 1, 3, 1. That's fine. And then the fourth vertex is supposed to have degree 2, but right now it has degree 1. And when you get here, what you discover is that there's no way to make this vertex have degree 2. To make V4 have degree 2 without messing up the degree of one of the other vertices. So it's just impossible, right? Like I can't add an edge like that because now V3 has degree 2 and it's supposed to have degree 1. I can't draw a loop because now V4 has degree 3 because the loop counts double and it's supposed to have degree 2. And so it's just impossible to do. That's all that it comes down to. So this one is actually impossible to do. So this is, I ended up with 1, 3, 1, 1. 1, 3, 1, 1 is fine. 1, 3, 1, 2 is not fine. So 1, 3, 1, 2 was not a possible sequence of degrees. Okay, so that is the idea behind the handshaking theorem and degree sequences and so on. So you do have questions like this in the homework, and probably also on the exam. I mean, they're not hard or anything. Just has to do with even numbers and odd numbers. And yeah, so that's going to be it for this first part of the lecture, because I'm out of time, and I will film and post a different set, a different lecture for the rest of the section later today. All right, so I think that's it for now. Talk to you guys later, where we'll finish this up.